All right, everybody, come on in. Have a seat. So, have a seat. I know talking with your group is so amazingly exciting, but so what I want to do today is I want to pick up where we left off, and voila, we actually have my laptop working again, which is awesome. We'll give a shout out to Vince in the ETS who managed to get everything working. But I did finally, I also blew it up to full size. I don't know if that's going to give problems with people seeing the bottom here. We'll see how that goes. But all right, so if you recall from last time, oh, and by the way, I apologize. I guess the screencast from last time, the video or the audio cut out after a while. I guess it went into the ether. But if you remember what we were talking about, we were talking about this Unix or POSIX notion that pretty much everything is described as a file. So devices, network sockets, interprocess communication like pipes, and files, of course. Now, okay, settle down. So that means pretty much that everything is based on open, read, write, and close. Now, obviously, not everything is a file. So what does that say? First of all, it does say that there's often something called an ioctl or an ioctl, depending on how you want to pronounce it, that you can execute on the file descriptor after open and set a bunch of unique things. Like if it's a display, maybe you set the resolution and so on. Those are the things that sort of break outside of the everything looks like a file paradigm, and in that case you use that special ioctl system call to set those things. But because of everything looking like a file, it means that things can be composed, among other things, with pipes. Now, by the way, I've heard some rumors that people doing homework 3 have hard-coded like only 2 pipes. You shouldn't hard-code. Okay? It should be able to deal with as many pipes as are up there. So you might want to look at your code again. The other thing is there's a very good question that came up last time, and I wanted to highlight the answer. Just because it looks like a file doesn't mean it's a file. So, for instance, pipes are only buffered in memory. They're never written to disk. Okay, network sockets are only buffered in memory or in the network. They don't get written to disk. Okay, so if it looks like a file, it's not necessarily a file. All right, are there any questions on that? Pipes are totally in memory. Okay? So you shouldn't be implementing pipes as files. Now, we talked about a bunch of I/O design patterns last time, including all of the F versions, fopen, fread, fwrite, which are libc. Those are the streaming versions, and then the native system call versions like open, close, read, write. We talked about the distinctions between those. As a little bit of a aside, it turns out that the fopen, fclose, whatever, those are man section 3. System calls are man section 2. So when you do a man on fopen, just look, it'll tell you it's section 3 versus section 2. So these were the patterns, right? Open before use to do access control. Byte-oriented. The operating system provides no format specification on the data. It's up to the user. We explicitly close when we're done. Among other things, that often flushes data out to the operating system. If you forget to do an fclose, you might actually lose some data. Reads are buffered, so when you do a read for so much data, it'll block and put you to sleep until the data's ready. Writes are buffered, okay, so you can do a write and immediately return even before it's been committed to the underlying device. And we also had a discussion about errors being relayed in various ways. One of the biggest ways is the return of something like a -1, and then you have to actually look at the error. There's various ways to look at what error resulted, okay? So don't forget to check your errors. The other thing we talked about was device drivers. And if you recall, because we have the standardized open-close read-write interface, but a lot of different devices underneath, we have to somehow match chaos with order. Okay, and the way you match chaos with order is with device drivers. The device drivers have the device-specific information and routines that know how to access the underlying device, and they typically have a top and a bottom half. The top half provides an interface upward to the kernel system call level that basically implements standard cross-device open-close read-write. There's that ioctl call here. By the way, that's how you spell it. I've always called it ioctl. That's how I was taught. Some people like to call it ioctl. I don't know. The other thing the device driver typically has is a strategy routine, which is the thing that starts everything. So if you're going to set up some disk operation you call strategy, then that actually causes the disk to do the thing. All right? Not too many of you are going to get to write device drivers, but at least not in this class, but it's actually very detailed and ultimately very satisfying if you get it to work. So that's something, if you were in a company and you were designing a brand new device that was going to plug into standard operating systems, you would absolutely be writing a device driver or having somebody do that. The top half, like I said, is the standardized portion. The bottom half runs as an interrupt routine and handles the fact that the device says, well, I'm done, or here's your data. And I gave you this sort of life cycle of an I.O. request briefly last time, where I showed you, for instance, up in the top left, the user program wants to do some I.O. So remember we gave the web server as an example. Maybe it's reading from disk. And so it makes a request, maybe for fread. Fread then calls read, which crosses the system call boundary. And what is the first thing that the underlying kernel I.O. subsystem does is it says, well, can I satisfy this right away without asking the device? Now, why might that be? Why might it be able to satisfy right away without even talking to the device? Yeah. Yeah, so it's buffered or cached already, right? Because the disk has, say, 4K blocks. You might be reading a few bytes. Those 4K blocks might be in the disk cache. We'll talk about that when we talk about file systems. If the answer is yes, you just return and everybody's happy. If the answer is no, now we got to start involving the device somehow. And so what we do is we start packaging up a query to the device driver and get ready to block the process, the user program that made the request. Why? Well, it's got to go to sleep because, remember that order of magnitude, how many instructions are lost when you talk to a disk? 1,000,000. Okay, right? At least 1,000,000 instructions worth of time. So you put things to sleep in the top half. So now the process itself is asleep, but the device driver is issuing commands to the controller. It's going to call the strategy routine. And then the device takes over. And by the way, the device may take a long time, but because we've put the process to sleep, voila, other things are running. Okay, so hopefully you're overlapping that I.O. with something else. Meanwhile, back at the fort, the device completes, says, oh, I'm good, generates an interrupt. Okay, so you get an I.O. completion interrupt. The bottom half of the device driver gets the interrupt, and now it decides what to do, like it might execute DMA, direct memory access. We'll talk about that later, where it says, oh, it tells the device, the disk, okay, copy that new block you just read into this part of memory. Okay? Anyway, so that's handled by the bottom half. When that's done, the bottom half figures out what to match, which process to match up with, and who needs the data, at which point we transfer the data into the user's buffer, and we put them back on the ready queue, and they're ready to go. And then they wake up and they run. Okay, and so this is a pretty general life cycle, and there's a couple of crossover points, especially in the first area here, where the kernel already has the data and can bypass talking to the device. All right, were there any questions on this? I talked about this pretty quickly last time. We good? Question?
One question with this was, so device driver bottom half is receiving interrupts and handling them separately. Does that have its own interrupt vector separate from the kernel?
So that's a good question. The question was, does the device driver that's getting interrupts, does it have its own interrupt vector separate from the kernel, was your question?
With the drive, or the actual device that has the driver on it.
So what I would say is every possible source of interrupts has a separate vector. And so, for instance, a disk drive or a particular disk would have a vector to come in on. The timer interrupt comes in on a different vector. I don't know if that answered your question. I think so. Okay, good. Any other questions? So now, what I want to do is so we're now happily reading and writing files. But what I want to do is I want to push this idea that everything looks like a file a little further. So why couldn't we communicate via processes as a file, right? So here's two processes. We have a file descriptor that we've opened for writing on one side and for reading on the other, and we do a write operation, and we read it on the other side, and voila, we've just communicated. Okay? And so the producer and the consumer of the file could be separate processes. That shouldn't surprise anybody here. That's the whole point of a common namespace where you open the file in both processes, and one of them's reading and one's writing them. And maybe they're separated in time or not. However, what if you're only writing all of that data once? It seems like a big waste to go to all the trouble of pushing it onto the disk and then reading it off of the disk. And so wouldn't it be nice if when we're communicating between two processes, we actually have something that looks more like a queue in memory? Okay, now this is going to feed back to my little red statement that just because it looks like a file doesn't mean it's a file. Okay? So this kind of inter-process communication, we would like to look like a file from a read and write standpoint, but not actually be a file. And among other things, what if it's not on the same piece of hardware? So there's a little cloud in the middle. Okay? On one side, we've got San Francisco. The other side, we have, Beijing. And what happens is you write on one side and you read on the other, and communication has happened. Ta-da, right in the middle. So we want something, an abstraction of a queue thing that looks like reading and writing on either side, but goes and goes across machines somehow, maybe across the world. So these are like connected queues over the internet. And when we think about it, however, we now have to ask the question of, well, what's the analog of open? In a file system, you open a file name /this/that/// foo.txt. That's a name, and the namespace of the file system you do opens it to that namespace. Across the network, it's a little trickier. What's the namespace, right? How are they connected together in time? It'd be great if when I write to one side and try to read from the other, that those two queues are somehow connected together, right? If they're not connected together, I'm, wasting my time here, okay? So the question is going to be, how can we make this abstraction work? Now, one particular reason this might be useful is a typical request-response protocol. So what do we look like? Well, we have a couple of these virtual queues. The client issues a request, which is a set of bytes in some format that you've decided on, like maybe HTML, writes that request, and it goes in this buffer, and what happens is it's going to issue a read for the response on a response queue, and now it's waiting. Okay? And so the client has issued the request in one queue, it's receiving from the other, and we'd like this all to work properly. Like, for instance, there's something on the other side, call it a server if you like, that's able to read the command, service the request, maybe with the local file system, write the result back, and then when that result comes back, it gets matched up with this read, which has been waiting. We copy the results into the user's buffer, and we wake up that process, and we keep going. Okay? That's a protocol. Not surprising to you guys too much because, I'm looking at a web server or something else. Okay? Lots of interesting IoT devices, by the way, have what's called a REST-style web protocol that basically allows you to use a protocol like this to cause it to do something, like open that door or whatever. Okay? Now, of course, we're really talking about these virtual queues across the network. Okay? So far, so good? Now, the question is, what is the equivalent of open? So if you notice, whenever I'm doing write and read, I have file descriptors. File descriptors are what type of entity? What do they look like? It's an integer, right? It's an integer that comes back from open. So what do we do here? So just as an aside, so client-server models look like this, where potentially you have many clients and a single server. And so you want to make sure that however we set these queues up, that if there's 12 clients talking to a server and client A makes a request and client B makes a request at the same time, somehow when the server sends a response back, they go to the right client. Okay, so there's got to be some demultiplexing thing here as well, just to point that out to you guys. Okay, and this is a pattern for many things you're used to. You know, file servers, web, FTP, databases, the cloud, whatever. So, what is a client and what is a server? So here is one. By the way, you could get many different answers if you were to ask 12 faculty in a room what a client and a server were, but they might look sort of like this. So a client is sometimes on. A server is always on. So the client initiates a request to the server services requests. For instance, a web browser on your laptop or phone. You know, your phone might not always be connected. You're walking through the forest, okay? The server is supposed to be always connected, okay? The client generally, although when we start talking about peer-to-peer communication and some interesting things later in the term, this won't be true, but in general, the clients don't talk to each other. So your phone isn't actually ever talking to somebody else's phone. What happens when you text? Well, it goes to the server, and then the server pushes it to the other person. So you're not actually communicating from client to client. It's a client-server, server-client thing. Okay? And then finally, the client needs to know something about the server in terms of its address, and the server needs to have a standard address. Otherwise, you can't match these two up. So this is the question about how do we connect these two endpoints together. Okay? So, how do we do that? Socket. What's a socket? All right? We're not talking about something you find in a garage to take your wheel off the car, right? A socket's an abstraction of network I/O. It's a mechanism for inter-process communication. In fact, inter-node communication. It's one side of a communication channel. So when you talk about a socket, typically two sockets get bound together, and now you got a full communication channel. And what you should know is sockets came from Berkeley. Okay? Woo. So BSD Unix, Berkeley Standard Distribution Unix, was known for many things, many new revolutionary things that lots of people cared about. 4.2 was particularly important because it had a bunch of new things. It had the fast file system. We'll talk about that later. It had sockets for the first time ever. And as I understand it from people that were there at the time, what actually happened is people were putting the 4.2 release together, meaning final checks, put it all together on tape. Yes, they did use tape. And there were actually runners from companies waiting to get the tape to run it back to their company and load it. There was so much excitement about 4.2 BSD. So sockets are Berkeley, okay? The idea behind a socket is the data transfer is much like a file once you've connected them together. So we're keeping with the standard POSIX idea that you open things and then you do read and write just like you would to a file, except that now we're going to be talking into an endpoint which emerges on the other side of the world potentially, right? And the socket idea is general, so it can be over any kind of network. So it could be two endpoints that are on the same machine. That's typically called a Unix socket. It could be over the internet, TCP/IP, UDP/IP. And then there's many other types of networks. Okay, OSI, AppleTalk, SNA, IPX, SIP, NS, many other options. Sockets can connect over those. Now, in this class, you're pretty much going to be using TCP/IP or UDP/IP, okay? But just so you know, sockets are really intended for this more general idea. And so here's an echo server. So assuming that we've managed to connect two sockets together, the idea here, for instance, the client issues a get-s from the standard in for a user. The user types a bunch of stuff that gets written. It goes in one end of the socket. It emerges on the other side. The server has done a read. It's now sleeping, waiting. It gets that read, prints the result out, writes the result to the different file descriptor, which comes back, gets read at the client side, and we can loop forever and basically echo everything you type here, goes out and comes back. Now, things to notice about this is notice how I've got file descriptors, okay, that I'm reading and writing from. Typically, when you set up a socket connection, it's actually bidirectional in many cases, so you can read and write from the same file descriptor. In one case, it's going out when you're writing. The other case, it's coming in when you're reading. Okay? Right? Are there any questions on this topology? This general idea? Yeah. So the essential difference between sockets and pipes. All right, so this is an argument that's had by many people. So one option could be to say that a pipe is a type of socket. Okay? However, usually the pipe implementation is sort of optimized for one-way communication, and it's sort of specialized for just local communication. But you could very well view a pipe as a type of socket. And in fact, where it is exactly that is if you use what's called a Unix socket, then you can have two endpoints where when you do the connection between the two of them, there's actually a little name that's placed in the file system. And the file system isn't for reading and writing the file. The file system is for them to learn about each other. And a Unix socket that's connected would look just like a pipe from somebody using it, but would be going through the full socket mechanism. So I guess the answer to your question is, on the one hand, you could say, well, a pipe is like a specialized socket. On the other, you could say, well, but it's really so specialized, it's often a separate implementation. But conceptually, they're very similar. Okay? And I will tell you that I know that TAs in this class have had arguments about is a pipe a socket or not. So there's a philosophy involved there. Okay, good. Now, so how would that server actually look? So let's start looking at some real code here, right? So the client has the file descriptor of the socket. So somehow we've opened the socket and connected it. I haven't told you anything about how that works, okay? So somehow these are connected. Trust me. But that file descriptor comes in as an integer. I have a buffer for sending and receiving set up. And what I do is I call this get request thing is some other code I'm not going to show you that just says, oh, user, please tell me what to echo. And then what we say is we're going to write the data that was given to us in the socket, so it's going to go out one side. We're going to clear out the receive buffer, and we're going to read. That read is going to be blocking and wait until something comes back. So that'll go to sleep. Eventually it'll come back. We'll find out how many bytes we got. We'll write to standard out. We'll get another thing to echo from the user, and we'll keep looping. So all this thing does is it asks the user for some phrase. It writes it to the socket, waits for a reception, prints it on the screen, goes back. Okay? Good? What happens the other side? Well, it looks essentially the same, right? Now, here, basically all the server's doing, however, since it's not got a user on the server side, it just says wait. So this read will go to sleep and wait until we get data. If there's no data, it'll exit. Otherwise, we'll write the output to the screen, and then we'll write it also back to the echo server, and we'll keep looping. And so what you see here is this write causes data to go to that read, and this write causes data to go to that read. And so we've got a bidirectional socket channel that we've set up. And we've got an echo, 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 echo. Okay? Questions? Now, what assumptions are we making here? Okay? First of all, somehow this thing, this channel with two endpoints that we've connected together is reliable. Just like when you write a file and read it back, the assumption you make is you haven't lost anything. The same idea is if you have a TCP socket. Okay, we'll talk about TCP in more detail later in the term. But you write to one side, you read from the other side. It just works. Okay, you don't lose anything in the middle, and it's very much like a pipe. No surprise there. Okay? And it's an in-order sequential stream, assuming we've set up TCP. So if you write A, B, C, D, E, F, G, you could even write A, B, and then C, D, and then E, F, G. What comes out on the other side is A, B, C, D, E, F, G. Okay? So it's a stream of characters. There's no actual boundaries that are enforced here. So if you want to send messages, you have to come up with a protocol that says something like the message has these many bytes and here they are. That's up to you. Okay, because remember, everything's a byte, kind of in the Unix philosophy. So if you want to do something more interesting than everything's a byte, that's up to you. How do we know when we're ready? Well, the file read gets whatever's there at the time, and basically we return, but we wait until something's there, just like a pipe. So if you go to do a read on a pipe and there's no data, it sleeps. When there is data, you wake up. Okay? All right. Questions? So, midterm 1, a week from today, in case you hadn't noticed. Yeah. All right. So this will be great fun. We have 5 rooms that we're going to be using. Unfortunately, it's a lot. We're going to put up an assignment of probably last name to rooms. We'll let you know how that goes soon. There's going to be a review session Tuesday here. So if you feel like you want to have a review session, which I'm sure you do, bring an extra like granola bar or something, because basically you get to listen to the amazing lecture on Tuesday, and then you get to be here for an hour and a half afterwards. So sorry about this. This was the room we got. The lecture may or may not be amazing, but the review session, that will be amazing. The other thing that I didn't put in the slide here is homework 3 seems to be a little longer than maybe we expected. So we're going to let you turn it in on Monday. However, you have to fix your code so it can have as many pipes as type. Okay, there will be some new tests available. Your code should just work with an arbitrary number of little vertical bars, okay? All right. Now, any questions? Material that's going to be covered is basically everything certainly up to today, and possibly what's on Tuesday might be in scope, but less detailed than what you get tonight. So, all right. So everything we've talked about in class is fair game. Good. Now, let's finish up this discussion of sockets here, which is how do you actually create these things and connect them together? So the thing about file systems is they're a bunch of permanent objects. They're in a permanent namespace. So to connect with a file, you just need to know the file name. That's easy. Okay, so files exist independent of processes. That should be no surprise to anybody. Sockets seem a little weird, right? There's something else. They're a means for processes to connect with each other, but sockets don't necessarily, in fact, they don't exist independent of processes. So when you set up a socket, it's a little different than just having a permanent name. So creation and connection is a little more complicated. But when we're done, we've got a two-way connection between two endpoints that we can send data in both directions. So, how do we name them? How do they connect with each other? So you got something in Beijing, you got something here. Somehow those two things talk to each other. Voila. That's pretty cool, but how does that work? All right, so that's going to be our question. Now, what is the namespace for communication? Well, basically we've got communication, which is IP is the protocol these days. There were many of them in the old days, but TCP, well, actually IP basically took over as the one that is all over the world. So in IP, we have several different namespaces. Among other things, we have the domain namespace like this, www.ecs.berkeley.edu. That is a domain name that describes an IP address. An IP address is, for instance, this 128.32.244.172. This is an IPv4 address, 32 bits, describes a destination on the internet. What is finally happening after 25 years is IPv6 is kind of showing up for real. Okay, that's 128 bits instead of 32. But most of what you are communicating still are these 32-bit IPv4 addresses. Okay, IPv6 is pretty much a sore spot. If you take 168, they probably have a whole section about how IPv6 took too long to show up and whatever, but we'll deal now because it seems to be there. So the other thing is so an IP address is like the name of a host. So right now, this laptop is tied in with the Wi-Fi. It's got an IP address. That's its current identity as far as the world is concerned. Okay? But naming a piece of hardware isn't enough. Okay, why not? Well, because there are many processes on that hardware. So just throwing packets at my laptop doesn't really do anything useful because which process is it destined for? Okay, now remember we had all these queues set up. We got queues and they represent processes, and it'd be nice if when I send a packet to a particular IP address, it'd be nice if I knew which process it was supposed to go to. That's the job of ports, okay, in at least TCP IP and UDP IP. And ports are 16-bit things, okay, right now. And the port numbers, so 0 to 1023 are so-called well-known ports, okay. Oftentimes you need super user privileges to bind to one. And so, for instance, those in that namespace are ones you're well aware of, like web servers at 80, or secure web servers at 443, or sendmail at 25. So ports in that space are typically reserved for standard services that you're used to and use every day. Ports from 1024 to 49151 are actually also registered as sort of additional ports for different services. So there's a lot of interesting services in that space that are that have been dynamically assigned over time. You can take a look. You should try Googling TCP/IP ports, and you'll actually see a table of all the interesting ones, including the ones that are well known and the registered ones. The last little bit are sort of called dynamic ports, and we're going to talk about those in a second. But the way you set up a connection that's unique is you need to have a unique IP address and port on either side, and the client basically needs sort of a random port to represent itself, and it typically comes in this space. I'll say more about that in a second. So let's look at how we actually set up a socket over TCP/IP. So first of all, what we do is at the server side, we set up a server socket that's ready to accept new connections. That server socket is sitting there on the remote IP address with the remote port, okay, and says, hi, here I am. And what it does is it executes what's called a listen system call, and the listen system call is literally listening for somebody who wants to connect. And what that means is here's a client. Let's suppose the client's trying to talk to the web server. It knows that that server socket's got an address, 128.32.161.43. I just made that up. And it knows that it's a web server, so it's port 80. So what happens is that client generates a socket, requests a connection to that IP address port combination. The server socket says, I hear somebody requesting. I'll accept it. And here's the fun part. Now it makes a brand new socket on its side just for this brand new connection, and then it connects them together. So says, okay, I've got you covered. And when you're done, you now have two sockets bound together in a way that they will communicate with each other, and it'll just work. Okay? So notice it's a three-phase protocol. Okay? So the server socket's a very special type of socket. It's not used for communication. It's just used for connection. You set the server socket first. So first phase is a request of connection. Server socket decides, it makes a new socket. It says OK. The client socket says OK. After 2 OKs, we're good. So it's 3 phases. 1, 2, 3, and we got 2 connected sockets. All right? Question? Yes?
How much memory does the socket take up?
Not very much. Mostly the socket memory is the buffer size. So however much buffer space you choose to allocate as part of the socket. Okay, so we might be talking a couple of kilobytes or something, or more if you set up a bigger socket. So basically, the server socket is something you probably hadn't thought of before, but it's basically listening for new connections, produces new sockets with each unique connection as a 3-way handshake. So here's a couple of things to remember. A unique connection, which is the yellow thing there, has it's a 5-tuple of values. It's a client address and a client port on one side. It's a server address and a server port on the other side, and a protocol. So if you have 5 things, that's a unique connection between 2 green items with yellow in the middle, as on that screen. What's a protocol? A protocol is something like TCP or UDP. Okay? And again, the client port is often randomly assigned, done by the OS during client socket setup. And the server port's well known, so like 80 for the web, 443 for secure web, etc. Questions? All right. So here is what a web server might look like in concept. So the server creates the server socket, binds it to an address, which is a host port combination, and does a listen, and goes into a loop with what's called the accept system call. So this is a blocking system call that the server says, okay, only return to me when you have accepted a new connection. Okay? Meanwhile, the client creates a socket, and it knows what the host port is for the server, so it's going to do a connection. So we have 1, 2, 3. Right? 3 phases, and when we're done, we have connection socket on either side, and now we have a communication setup. Notice the listen socket's still going to be there, so more connections could come in if we choose to accept them. We get 1 socket on the server side for every accept that we execute, and that gives us the file descriptor for the new socket on the server's side, and that's our connection. Okay? And so then, for instance, the server might execute a read on that socket. Well, there's nothing in it yet, so it blocks. But the client does a write on its side of the socket. The data goes across the country or wherever. And now that read request may be interpreted with some data. It does a write response. The client is waited. You can do this many times. And now, voila, we can have a protocol. Client requests something, server gives it back. Client requests something, server gives it back. We can do this over and over again, and suddenly we have a web server. Okay? And when the client's done, it closes the socket, server closes its socket, and then it can go back and do another accept. So in concept, this is a web server. There's a couple of pretty serious problems with this. Among other things, it's serving exactly one thing at once, right? So that seems kind of bad. Everybody see that? I do one accept, and then I handle my protocol, and then I go back and do another accept. And so this particular skeleton that I put up here doesn't seem quite what we want, but it gives you all the ideas. Okay? Now, here's an example, the client protocol. Okay, and you'll get more and more used to this as you go. But for instance, what does an address inside of your code look like? It's what's called an addrinfo structure. Lookup host, I'm going to show you in a second. This is some code that we're going to write ourselves. That we say, well, here's the name of the host and here's the port. Find me all the information that the socket's going to need to make the connection request. Once we've got that, we allocate a brand new socket with some of the stuff that came back from lookup host, like what family are we dealing with, like AF, the IPv4 family. What type of socket? Maybe it's a stream. What type of protocol, like TCP, whatever. That gives us back a file descriptor. Ooh, now we have a file descriptor that perhaps we can do something with, like read and write to. Okay, remember that? Standard, open, close, read, write paradigm. But we can't really do anything with it until we've done connect. So when we do connect, that's the point at which the client reaches out to the server socket and says, hi, connect me, please. And assuming that that succeeds, connect will block until it does. When connect returns, now we're connected. Now, of course, there's an error you got to look at, right? Everybody's always got to look at the error coming back to see whether there was a failure there. I'm not putting the error up there for make this quick. But once we've got our socket, now this run client code, I don't know what it does. It makes requests, whatever. It can read and write from that socket because we're connected to the other side now. Okay, and then when we're done, we just close it. Okay, so open, read, write, close. Boy, that paradigm there is pretty standardized now, right? It's just how do you connect the socket? Well, it has to do with addresses. And by the way, getting the server address for the client might look like this. And I'm going to have you stare at this a little bit later and do man on the various things. But basically what we want ultimately is this addrinfo that describes everything the socket needs. And the way we do that with this get addrinfo is we put some hints that say, well, it could be either IPv4 or v6. We want it to be reliable. And then the host name and port name and some pointers to hints and server get sent out, and that actually invokes things like DNS. Find me where the host is. What's its IP address? Is it an IPv4, IPv6, etc.? All that stuff gets loaded into the addrinfo and gets returned back so that when we run this code, this connect does the right thing. And if the address resolves to IPv6, it'll connect through IPv6. If it resolves to IPv4, it'll do that. Okay, and by the way we allowed ourselves to do either is we say address family unspecified. Okay, but all right. Server side. Okay, again, not as complicated as it looks here. We need an addrinfo. Assuming we've got an addrinfo that says this server is going to be on a certain port locally, then we get ourselves a socket. We bind it. So what that says is take the socket, attach the address to it so that you can listen on it. So we're not trying to request. We're trying to bind an address to it. And then we execute listen. That's that little ear, right? And so now the listen socket, called server socket, is busy listening for an incoming connection. And we go in a loop. And we say we try to accept on the server socket. This accept will block and the process will sleep until a new connection comes in. When the connection comes in, we get a connection socket. So the server can now talk to the connection socket. So client got a client socket, server got a server socket, they're connected, and now we can read and write whatever protocol we want. That's up to you guys, okay? However you want the bytes to look. They could be serialized in some format, okay? They could be text. They could be binary. It's totally up to you. Of course, if you're using the HTTP protocol, it's probably like HTML or something a little better defined. Yes?
So, theoretically, sockets apply to any sort of internet protocol you could like, right? But in this case, it seems like they're handling everything up to layer 4. Like you write something abstract out of sock stream, whatever, and it picks IP and TCP or UDP.
Yep.
It handles all of that.
It handles everything, including the reliability portion of TCP. Correct. And so what I'm writing and reading from are just streams of bytes which go in one end and show up on the other. Yes. Correct. All right. So it is actually pretty easy to use sockets. Again, there's a lot of stuff on the screen here, but once you sort of get used to what stuff to focus in on, there's not a lot going on here. It's just you got to get it right. Yes.
So for UDP, there's reliability within a datagram, right? There's a datagram size. The datagram either arrives or doesn't, and so it's discrete. But here we're writing a stream of bytes.
Yeah.
And, so is there? Are you just sort of supposed to write datagram size streams of bytes at a time?
Okay, good question. So, if we didn't use sock stream, but we asked for datagrams instead, you're right. The packets get sent as a chunk, and they either arrive or they don't. Okay. Now we've been talking about the paradigm of open, read, write, close. It turns out there's also some system calls which you should look up called send message, receive message, and you can do that, and they will packetize for you, right? Or on a stream, what you can do is you can build your own packet format, which says a packet format, it's a serialization format that starts out by saying the following thing has this many bytes, and then you lay out the bytes, and so on the other side it first reads the length, and then it brings the bytes in, and so on. And you can do that with a stream because it's reliable, and what will happen is when you do your reads and you say, give me this number of bytes, it'll block until you got all the data. So you're packetizing, again, that's you, get to packetize any way you want, but fundamentally with a stream, it's bytes in, bytes out, and if you want anything more interesting, which mostly you do, you got to do it yourself. And of course there are libraries and lots of stuff to do interesting serialization on top. So when I say do it yourself, I mean do it with something other than what the socket gives you. All right? Good. Anything else? Okay. So, by the way, the one different thing about this server setup for an address for listen sockets is often you want to, your hint should have this AI passive, which basically says you're setting up an address that will deal with listen instead of binding. And also this null value here, typically I'm not saying what my own host name is. Instead I'm saying, well, whatever IP addresses I happen to have, as a host I can actually have more than one, I will bind to all of them. So anybody who wants to come in and knows any of my addresses could come in. Okay, and so that's what I do by not actually saying what the host is. Okay. So let's finish this up a little bit. How does the server protect itself? Well, we want to isolate the handling of each connection by forking off another process. So here, all I've done that's a little different is once I accept the connection socket, then I fork, and the child does the communication. And what the parent does is it busy waits until the child exits, and then it goes back and accepts another. So what I've done here is I've isolated the server processing in a separate process, like a sandbox. And the parent waits, and when that sandbox is closed, I'm done. So now this doesn't solve the I want to have multiple requests going on at once, but what it does say is it says I'm going to isolate things in a separate process as a way of protection, for instance. Okay. Now, how does that look? Well, pretty simple. So server protocol version 2, we still do our listen, we get our accept. I fork a brand new process. Here I am in the child process. The first thing I do, remember what fork does? Fork copies all the file descriptors and gives you access in every process. So the child closes the server socket. Why? Because the child's not listening. The server is, or the parent is listening. The child is just communicating with the connection socket. So the first thing the child does is it closes the server socket, it does its thing, and then it closes the connection socket, and then exits. What does the parent do in this particular code? It closes the connection socket. Why? Because the parent doesn't care about the communication going on. The parent is just setting communication up. And it does await, and then we loop. Okay? So that's that paradigm, by the way. When you fork, you typically you duplicate all the file descriptors, and some of the file descriptors make sense for the child and some make sense for the parent. This is a little bit of a hint about homework 3, right? Sometimes it makes sense for the parent, sometimes it makes sense for the child. Wax on, wax on. Okay. Now, of course, the thing we might still want to do with this is make this concurrent. I'm not going to push this much farther, but the problem is if you got a really nice website, lots of people want to look at it. Okay? You're going to get slashed on it or something else, right? So, something on Reddit, right? So what happens is that I would like to have many parallel requests going on at once. The listen system call, which listens on the server socket, actually has a queue of incoming connection requests. And every time you have an accept, you pull another one off the queue and make a connection. Well, the queuing is happening in listen, but we're not allowing more than one thing to happen. Well, what do? We just allow more than one thing to happen. Okay, so this diagram looks almost identical, except at the point that I fork, the parent closes that connection socket because it doesn't care about it, and it goes back and accepts something else and forks another guy. So this is a way of getting parallelism where we fork a brand new process for every incoming connection, and they're all running in parallel. Okay? Notice how I just changed a tiny bit. And if I actually looked at the code here, I put in one interesting issue here. So if you look at this code, it looks identical to the server version 3, except I commented out wait. Right? Don't wait for the child to exit. Except the problem with doing that, is we got zombie children, right? Because if the child processes exit and the parent doesn't get their wait state, we got a problem. Okay, and so one of the fixes for that is the signal sigchild, and for a lot of versions of modern OSs, if you explicitly set sigchild to sigignore, what you're saying there is I don't care about the exit status of the children, just let them exit and go away. All right, so then you don't have any zombie children floating around. Okay? Good. So, any other questions? Yeah. Now the parent, they're zombie children. So what happens is the child, for instance here, when it's done, it exits with an exit status of some sort. And that, basically when you exit, you free everything up, except you've still got to be able to get that exit status to the parent somehow. So the process control block is stuck in a zombie state because it's got to hold on to that exit status until the parent executes wait and gets it back. And so basically by saying I'm ignoring sigchild, or the other thing you can do is you can have sigchild be trapped, and then you can do a wait to get the exit status and figure out, there's a version of wait with a bunch of arguments, you can figure out which child it was and what their exit status was. That's another way to get rid of them. Right? Okay. No zombie parents, just zombie children. All right. Great. So, now what we're going to do is, I think we're going to take a brief break, but before I do that, I want to put up, right here, hold on, I got to find it, there it is. There we go. All right, give you guys credit for being here. Go ahead, fill out the form. Kitten. And by the way, this hat is tan. This is why we give you a little credit for showing up, okay? Welcome. Thank you. All righty. So, we are going to switch gears and switch into a different topic, which is scheduling. So, if you remember, on the first day or the second day, we kind of had this question of, if there's a ready thread, select it and run it, otherwise run idle thread. Somehow in the scheduler, we pick the next thing to run. And let's push on that a little bit. So what thread should run on the CPU next? We're going to talk a little bit about some of the goals and policies, and eventually we're going to look at a number of different schedulers. Now, we're not going to get all the way through this today, but we're going to take a good stab at starting on it. And if you recall from scheduling, we had this view where we had the ready queue and the CPU, and basically, under normal circumstances, what happens is things run on the CPU until, say, the time slice expires. We'll say more about that in a moment. In which case, it goes back on the ready queue. We grab something else to run. But there are many other queues in the system, like I/O requests. So you make a request to the disk, you get put to sleep on some queue related to that. And eventually, when the I/O is done, you get put back on the ready queue, etc. Also, when you have a fork operation, suddenly you have two things where there was one before. Well, one of them gets to run, the other one doesn't for a little bit, right? So the new child gets put on the ready queue, or the new parent gets put on the ready queue, all right? One or the other. So there's many possible queues, the ready queue being the one that goes immediately to the CPU, but there's a lot of other queues. And the question is sort of, how does the OS even decide which of several things to take off the queue? So imagine the ready queue's got 1,000 tasks on it. First of all, I would say that you've probably programmed this badly because you got too many threads and it's going to perform poorly. But let's ignore that for a moment. Suppose you got 1,000 things on there. Which one? Okay, now, obviously you could say, well, FIFO, we'll take the first one. Okay? And then the second one and the third one. Well, that turns out to not be a great idea. Okay? We'll tell you why in a moment. But scheduling is basically deciding which threads are given access to resources from the moment to moment. Often we think in terms of CPU time, but there are schedulers for the disk. There are schedulers for the network. There could be a decision of how much network bandwidth you're allowed, okay? And after you've gotten rid of your network bandwidth, you go on, okay? And so we're going to talk about other schedulers, but we're going to start with the CPU. Scheduling's all about queues, okay? So, what are some assumptions? So scheduling was a really hot topic in the 70s. Now, I mean 1970, not 2070. And there are many implicit assumptions there, like, for instance, one program per user, one thread per program, programs are independent. If you think about this, this is not terribly, these restrictions seem kind of overly restrictive today, but it turns out if you do that, what's great is they simplify the problem so you can solve it. Like, for instance, maybe I can actually ask the question of what is fair? If I have a bunch of user programs running and I want them to have fair access to the CPU, what does that mean? Okay, well, if there's only one thread per program, maybe I give each of them an equal amount of CPU time, and suddenly that's fair. Okay? Except, what if, for instance, I run one compilation job and you run 5 on the same machine, and suddenly, do I want to give still 50-50, so those 5 jobs are running with much less CPU than the one job, or do I want to divide things in 6s? Those seem like both possible fairness questions, right? So the high-level goal is to dole out CPU time to optimize some desired parameters, but you've got to figure out what those are in the first place. Now, one assumption that we're going to take on part of this at the beginning here is this idea of CPU bursts. And if you were to look at typically an execution pattern, what you'd see is you do a bunch of stuff, and then you wait for some I/O, and then you do a bunch of other stuff, and you wait for I/O, and you do a bunch of other stuff, and you wait for I/O. Now, what is that I/O waiting for? Well, it could involve going to the disk, but it probably also involves things like each character I type, right? I type a character, it goes in, it runs a little bit, then it waits for the next character. And if I were to take a look at the pattern of how long we run with the CPU before we hit an I.O. Stopping point, we get this kind of pattern where it's weighted heavily to the short tasks, and there's a very long tail. Okay, so what does that say? Well, it says that most tasks are extraordinarily short. Why is that? Well, when you're typing, there's not a lot to happen when you type the J, right? It goes back, and then you type an H, whatever. So a lot of the I.O., which directly involves users, leads to extremely short burst periods. All right? Whereas if I do long computations, like compute the first 100 digits of pi, I'm going to be out on the long tail. Okay. So an execution model here is that programs alternate between bursts of CPU and I.O., typically use the CPU for a short period of time, do I.O., etc. Each scheduling decision is kind of about which job to give the CPU to use for its next CPU burst. Now, let's think this through for a second. Let's suppose that you get easily annoyed when you have to wait. How many people are like that? Okay. Now, suppose your CPU could give precedence to things that are happening on the screen and when you're typing, or it could give precedence to the compilation job that's been sitting there for 4 days. Which one do you want to avoid being annoyed? Typing, right? You want to give precedence to the short ones, not to the long ones. So you could say, just by thinking about this for a few moments, that one policy that might make a lot of sense if you have a combination of interactive and long-running jobs is to give priority to the really short bursting things so that the person typing doesn't get annoyed, right? Okay. Now, one of the possible things we're going to talk about is direct time slicing, which says you run something for 10 milliseconds and then the next thing and the next thing and the next thing. And what's going to be interesting about that is that's a way to make sure everybody makes progress, but it doesn't necessarily give the least annoyance factor. Okay, so there'll be other things maybe that we could do better. Now, I will point out, by the way, that interrupting long-running jobs may not be the best thing if what you really care about is getting that compilation job done as quickly as possible. If you want to optimize your CPU, cache, disk cache, and sort of all of the hardware parameters, maybe you really want to run those long-running things for big periods of time to get big efficiency out of your machine. Okay, and so you could imagine the schedulers that we have, or say the parameters we use for our schedulers in a laptop might be very different from the cloud, because in the cloud they're optimizing for throughput. On the laptop you're optimizing for interactivity. Okay? Good. So what are some goals or criteria? Well, many. So I could minimize response time. That's an interactivity thing, right? So response time is what the user sees, the time to echo a keystroke or so on. I will tell you, when I was a wee lad, I won't tell you how long ago that was, we had a time-sharing machine that a bunch of us were typing our papers on, and it was so overloaded that you would type something in Emacs, like, to be or not to be. I wrote that, by the way. To be or not to be, that's the question. And a minute later, it would go, to be or not to be, that's the question. That was annoying, okay? All right, if you wonder why Hamlet is a little strange, you can say that had to do with scheduling policy, okay? Now, we could also maximize throughput, okay? Like number of operations or jobs per second. If you're a big cloud service provider, you're trying to make sure that you get the most jobs done per unit of time because that's what people are paying you for, okay? And throughput's related to response time, but it's not identical. It's basically minimizing the response time will sometimes lead to more context switching than if you maximize throughput. So trying to make users happy, actually context switches more, has higher overhead. It's not as good for throughput. Okay, and so there's a couple of things to maximizing throughput, by the way, minimizing overhead, context switching, and then using the CPU resources really efficiently. And then, of course, you could also say, well, I care about fairness. I want to share the CPU among users in some equitable way. Whatever equitable means, right? So fairness is not minimizing average response time, because better average response time actually makes the system less fair. Because if you're typing really rapidly, you're getting a lot of CPU time, and so you're being, it's unfair because I'm getting CPU. Okay? And so I hope, by the way, that I'm going to say this several times this lecture and in the next, I'm hoping that you're getting an idea that just saying the word fair doesn't necessarily tell anybody anything, right? Because fair has a whole bunch of questions associated with it. What do you really mean by fair? It's really an optimization according to some policy that somebody's called fair. Okay? This is not a political discussion, by the way. So, let's take the obvious thing, right? First come, first serve scheduling. Okay? Or FIFO. Okay? Or run until done. Many names. So in early systems, the big machines, first come, first serve meant one program scheduled until done, including all of its I.O. And now first come, first serve really means keep running until you block on I.O. But the idea is pretty similar. For example, we have three processes. So process 1 runs for 24 units of time until the burst time's over. Process 2 runs for 3. Process 3 runs for 3. And we could say the following. Suppose these jobs arrive in P1, P2, P3 order. Okay, how many people know what Gantt charts are? You've seen these, right? They're for laying out time. So this is a CPU execution time with a FIFO scheduler where P1 gets to run for 24 units, then P2 runs for 3, and then P3 runs for 3. Okay? Now, if you are P2 or P3, you might be getting a little annoyed, right? And that annoyance, in this case, happens to happen because P1 arrived early, first. Okay? So if we were to actually compute waiting time, what we'd see here is, for instance, P1 waits 0, P2 waits 24, and P3 waits 27. So that's the amount of time waiting before you actually get to even execute. Okay? So you might ask, is that fair? Well, I would say P2 and P3 are probably not happy, right? Now, the average waiting time here is what I get when I sum them all up. I get 17 here. So now we can start talking about some metrics like waiting time and average waiting time that maybe we can optimize somehow to make better. Okay? Metrics mean optimization is possible. We can also talk about average completion time. So notice that P1 completes in 24 units, P2 at 27, P3 at 30. Why do I say P3 has an average completion time of 30? Well, because P3 showed up at 0, but it took it 30 units to get its 3 units of work done. Okay? All right. What we're really seeing here is something called the convoy effect. All right? Basically, short jobs getting stuck behind long jobs, which is kind of a fundamental property of FIFO. And so here's the convoy effect. So notice what happened here. We've got a short job running, and the green job arrives. It gets to run as soon as the blue one's done. Here's another one that arrives. Okay, we're kind of making nice progress. Notice how things are arriving. Suddenly we've got red. Okay, so the red job is long. But if our arrivals keep happening, notice what's happening here. We're building up. So all of those jobs arrived, and now they're stuck. Right? This is like buying milk at the supermarket. You go to the 5 items only, and there's somebody with a cart full of, potato chips or something, right? So the convoy effect is a real problem that shows up with FIFO. All right? Now, here, all I've done is question, yes? Well, we have to use very special materials that let us look into the future. Okay? And that the faster than light transistors that we're starting to put into our machines let us predict the length of time. No. You ask a really good question. How can we predict this? Anybody have any ideas? Yeah. So we could try to look at code. Yep. What else could we do? Yes. Yeah, we can look at number of instructions. Yes. Well, it's impossible to perfectly predict. But, yes? You could guess randomly. We won't do that. In reality, yeah, go ahead, one more time. Yeah, so what you can do is you can build a model. Heck, this is the machine learning era, right? You can build very simple models that look at the previous burst times of a particular task, and you can come up with a prediction of how long it's going to be. We'll talk about that in a few slides, okay? But that's about the best you can do. The thing to get out of the convoy effect here, by the way, is not that what I need to do is predict the future. What you should get out of this is if I'm stuck to FIFO ordering, I have problems that arise when big tasks show up. Okay, the convoy effect is a fundamental issue with this level of scheduling. Okay? All right? And by the way, that prediction of the future using simple Kalman filter technology or things that you guys have probably heard about in other classes is actually a pretty good idea. But we'll get there. So here's our example, for instance, of what happens if we just get a different order. Well, now, notice our average rating time is 3 and our average completion time is 13. We've come way down only because of accidental arrival order. So hopefully what this is kind of indicating to you is that perhaps first come, first serve is really not the right thing. Okay? So FIFO pro and cons are, one, it's really simple. So the great thing about queues is now you guys are experts in C lists, right? How many people think they're an expert in a C list? All right. The those of you that didn't raise your hand, I'll assume that you were just being modest, okay? So they're simple to implement, but the downside is short jobs get stuck behind long ones, right? And this is the trying to buy milk, stuck behind a large cart of items. The best part about getting stuck behind a large cart of items is you get to read the latest thing about space aliens. So, I don't know, maybe first come, first serve works out there or not. But let's see if we can do something different, okay? So the first come, first serve scheme, potentially very bad for short jobs, which is going to raise the annoyance factor, right? The short burst makes people annoyed if you're stuck with first come, first serve. And so what we'd like to do is something else. So we're going to try round robin. See the robin? No. Okay? Which is really about preemption. Okay, every process gets a small unit of CPU time, and then we're going to keep switching off. We're going to run for a little while, stop that guy, run for a little while, stop that guy, keep going. And often the process has a small unit of CPU time. We call it a quantum, and it's usually in the 10 to 100 millisecond range. Okay? And when the quantum expires, the process gets preempted, added to the end of the ready queue, and we pull the next one off and run it. Okay? So it's FIFO, but it's FIFO with preemption with a quanta. So it's a slightly more sophisticated. And end processes in the ready queue, if the time quantum's Q, what you could say is that kind of every process gets 1 over nth of the CPU time in chunks of at most Q time units. And so you can actually make a statement like this red one, which basically says that no process waits more than n minus 1 times Q. So I can put a bound on how much annoyance you've got. How long does you have to wait before your process of typing a character shows up on the screen? Okay, and I can do that by tuning my parameters. But I want you to notice something. Do you see where n comes into play here? If you've gone crazy because you love threads so much, you've taken 162 with Professor Kubi, and you just learned to love your threads. And so as a result, you put thousands of threads running at the same time because you've learned to love your threads. What does that mean here? It means n is really big. So even though I'm switching through stuff, my minimum, or my guaranteed time is still really long. And so too many threads means too much context switching, and you don't have much responsiveness. Okay? You see how n comes into play there? So, and the other thing to note is every time you switch, what are you doing? You're saving registers, you're restoring registers, you're changing the address space, you're entering the kernel, you're exiting. There's a lot of overhead. And so just cranking down Q to make it a millisecond or 100 microseconds or something so you're switching faster, what happens is now you're trading off overhead for some notion of responsiveness. But basically what you're doing is now you'll get to the point where it's all overhead. You're never computing anything, you're just switching. Okay, and there's a word for that. Anybody know what the word for that is? Starts with a T. Thrashing. All right. So, however, round robin is a pretty common possibility. What we can see here is that as Q gets larger, we kind of converge to FIFO, or first come, first serve. As Q is very small, we're interleaving. Maybe if you think of Q getting smaller than an instruction, we've got hyper-threading. I don't know, maybe. Q has got to be large with respect to context switch overhead. Otherwise, you're all overhead and you're wasting time, okay? So, for instance, here we have another Gantt chart where we've got a bunch of processes with their burst times, P1, P2, P3, P4. And the Gantt chart looks like this. Let's suppose our quantum is 20. So P1 runs for a little bit, 20. Why does it run for 20? Well, because its burst time is 53. So we get to the end of our quanta before we're done. And then P2 gets to run, but it only runs for 8, so it exits early. P3 runs for 20. P4 runs for 20. And now, after that first loop through there, we're done with P2, but P1, 3, and 4 are still running. So now we go back. And if we were to continue this, you could simulate this, right? You could figure out when each one of these things runs. Okay, everybody with me on that? And by the time we're done here, at the very end, we've hit cycle 153 or time quanta 153, and everybody's done. And notice that we could compute like the waiting time for P1 from when it first showed up to when it's done is 72, etc. Average waiting time is 66 and a quarter. Average completion time 104 and a half. And so round robin, the pros and cons are, well, pro is it's better for short jobs, so it's got a plus on fairness, of course, whatever fairness means. And the downside is the context switching can really add up if we're not careful. Okay? Now I'm going to show you a couple of more slides and I'll let you go. But how do you choose the time slice? If it's too big, the response time suffers. Oops, sorry. If it's infinite, you go FIFO, right? If it's too small, throughput suffers. So if I turn Q way down, it's all overhead and throughput suffers. I spend all my time switching and no time computing. Okay? The actual choices of time slices, this is a little amusing. So when Unix started out, they often had the swapping time was a second. So that's okay maybe when one or two people are going, but imagine two of you are typing furiously and it's putting your character up every second. You might get annoyed pretty quickly, right? So you need to balance short job performance and long job performance. And so a typical context switch overhead is about 0.1 millisecond to a millisecond. And so that's roughly, you want to be in the 1% range or so of the context switch time so that overhead is no worse than a percent. And so these typical numbers are about 100 milliseconds to 10 to 100 milliseconds for switch time. Right? Pretty standard. Now, let's see. Let's do one last slide here. Assuming zero-cost context switching, is round robin always better? So suppose you have 10 jobs and every one is 100 seconds of CPU time. Round robin scheduler quantum of 1 second. If you notice what happens here is if we run job 1 to its entirety, then 2, then 3, then 4, or we run job 1 for 1 second, job 2 for a second, job 3, job 4, we keep swapping around. Here's what things look like at the very end. If you think it through, we're going to have exactly 1,000 times quanta when we're all done. And what you find is that in this instance, FIFO is actually much better on our parameters because we're not wasting all this time switching. Because some jobs, like job 1, gets done early. Okay. So, in conclusion for now, we talked about round-robin scheduling, giving each thread a small amount of CPU time. Okay, pros are better for short jobs. Wait, so what happened here? Let's see, what do you know? Well, actually, I guess I don't have a summary today. Something screwed up there. But hopefully you got a good idea where we're going with scheduling. You have a good idea why FIFO is not what you want and what round robin's good for. I will see you on Tuesday. We'll finish up some scheduling discussion then.